Every year, millions of people swim in the ocean. They feel it sting their eyes. They accidentally swallow a mouthful and immediately regret it. And most of them, at some point, ask the most obvious question. Why is it so salty? The easy answer is minerals. The rivers bring minerals to the sea. But that answer raises more questions than it settles. Where did those minerals come from? Why hasn't the ocean gotten saltier over time if rivers keep delivering minerals every single day? And why is the ocean salty in the first place, when the original water on Earth, the water that came from comets and volcanic steam 4 billion years ago, was almost certainly fresh? The real answer is a 4 billion year geological story that involves volcanoes, ancient oceans, the chemistry of rock, hydrothermal vents at the bottom of the sea, and a balancing act so precise it borders on the miraculous. When Earth was young, we're talking 4 to 4.5 billion years ago, there were no oceans. The planet was a churning, volcanic hellscape, and the early atmosphere was thick with water vapor, carbon dioxide, and sulfur dioxide. As the planet cooled, that water vapor condensed and fell as rain. 4 millions of years. This early rain was slightly acidic, because it absorbed carbon dioxide from the atmosphere and formed weak carbonic acid. And this acidic rain fell on volcanic rock rich in minerals like sodium, potassium, calcium, magnesium, and chloride compounds. The acid slowly dissolved those minerals. And the resulting mineral-rich water flowed downhill into the low-lying basins that would become the first oceans. The two most abundant dissolved minerals were sodium and chloride, which, when they combine, form sodium chloride. Table salt. The ocean, at its most fundamental level, is a mineral broth that has been collecting dissolved rock for 4 billion years. Rivers continue this process today. Every river in the world carries dissolved minerals from the land to the sea. The Amazon, the Mississippi, the Ganges, all of them are constantly adding mineral content to the oceans, just as rivers have been doing since before the first fish ever swam. Here's the puzzle that stumped geologists for a long time. If rivers are constantly adding dissolved minerals to the ocean, and have been doing so for billions of years, why isn't the ocean getting saltier over time? By now, it should be far saltier than it is. The answer lies at the bottom of the ocean, in one of the most extraordinary geological features on Earth: hydrothermal vents. At mid-ocean ridges, where tectonic plates pull apart, seawater seeps down through cracks in the ocean floor and comes into contact with superheated magma rock. The water heats up to hundreds of degrees Celsius and is chemically transformed. During this process, the rock absorbs certain minerals from the seawater, particularly magnesium and sulfate. And the superheated water, now loaded with different minerals from the rock, blasts back out through the vents. This process acts as a giant mineral exchange system. The ocean is constantly losing certain minerals into the ocean floor through hydrothermal circulation, while gaining others. The result is a remarkably stable chemical balance that has kept ocean salinity at roughly 3.5% for hundreds of millions of years. There's also evaporation and sedimentation. As water evaporates from the ocean surface, it takes pure water with it, leaving the salts behind. Some minerals precipitate out and sink to the seafloor as sediment. The ocean is not a passive reservoir. It's an active, self-regulating chemical system. The specific chemistry of ocean water, dominated by sodium and chloride, isn't just an accident of geology. It turns out to be one of the most important preconditions for life on Earth as we know it. Marine organisms evolved in saltwater. Their cells, their chemistry, their entire biological systems are calibrated to function in a sodium chloride solution. The salt content of human blood, about 0.9%, is a direct echo of the ancient ocean. We carry the sea inside us. The sodium ions and chloride ions in seawater are electrically active. They help regulate the flow of electrical signals in nerve cells. They control the osmotic balance that keeps cells from bursting or shriveling. Without them, the complex electrochemical communication that makes a nervous system possible would not work. Some researchers have proposed that the similarity between blood plasma and ancient seawater is not coincidence. It's inheritance. The first cells evolved in the ocean. They built their internal chemistry around the chemistry of the sea. And when complex animals eventually left the ocean and colonized land, they didn't leave the ocean behind. They took it with them, sealed inside their bodies. The ocean's saltiness is not a quirk or an anomaly. It's the product of 4 billion years of chemistry. Volcanoes and rain and rivers and rocks and hydrothermal vents working in a slow, geological symphony to produce a solution that is both ancient and precise. That taste of salt when you accidentally swallow a mouthful of seawater? You're tasting 4 billion years of Earth's history. You're tasting dissolved mountains, ancient volcanic rock, and the accumulated mineral memory of a planet that spent billions of years building the precise chemical environment needed for life to arise. The ocean didn't just give birth to life. In a very real sense, the ocean's chemistry became life. And every time your heart beats, driven by sodium and potassium ions flowing in and out of cells, you're running on the same ancient saltwater recipe that started everything.